Hi everyone, so in the last video we took a look at the basics of graphs of polar equations with circles and lines. This time we're going to expand on that. We're going to take a look at the other types of polar curves, rose curves, cardioids, limaçons, and lemniscates. So let's take a look at some examples. Alright, so let's start part 2 of this video with example 2 from the guided notes. We want to sketch the graph of the polar equation r equals 5 sine of 3 theta. And this is going to be an example of a rose curve. And we'll see why it's called that once the graph is all said and done. So step 1 is the same as the step 1 from our circle equation from last time. Remember, what we wanted to do before was graph the sinusoid and then analyze the sinusoid to get the polar graph. That's what we're going to do with our rose curve as well. So let's graph the sinusoid. And remember, we talked about graphing in the theta r plane. So we're going to treat theta like it's your x variable. We're going to treat r like it's the y variable. So this is the theta r plane. And this is where we get the sinusoid. This is not our polar graph, but we're going to use the sinusoid as something that's going to help us draw the polar graph. So all I did was I rewrote out the equation there. R equals 5 sine of 3 theta. So if I look at r equals 5 sine of 3 theta, the period is going to be 2 pi over 3. And the amplitude is going to be 5. So my maximum is going to be 5. Minimum is going to be negative 5. So if I look from theta equals 0 to 2 pi, I'm actually going to have 3 full periods of my graph. So if I just sketch out 2 pi over 3 and 4 pi over 3, I'm actually going to get 3 full periods of my sine graph. And just sketch that in. It's just a sketch, it's not perfect, but it's going to allow me to graph the polar curve. So let's think a little bit more deeply about where I'm hitting 5, where I'm hitting 0, and where I'm hitting negative 5. So if we remember back from chapter 10, if the period is 2 pi over 3, the increment is going to be 1/4 of that. So if I take 2 pi over 3, multiply that by 1/4, I'm going to get 2 pi over 12, or just pi over 6. So that tells me that it's going to take me pi over 6 units to get from 0 to the top, another pi over 6 units to get back to the theta axis. So this is going to be pi over 3. And you can check the math here. This is going to be pi over 2. So if I go pi over 6, pi over 3, pi over 2, and 2 pi over 3, that'll give me a good start as to how I'm going to graph this. So let's get a start, and I can actually take a look at some polar graph paper here just because it requires a little bit more precision than our last example. So I'm going to start by labeling some of our angles. So I've got 0. Remember, each of these branches represents pi over 12 units. So pi over 6, pi over 3, pi over 2, and 2 pi over 3, and I'm just going to keep going every pi over 6 units, so 5 pi over 6, pi, 7 pi over 6, and 4 pi over 3, right? 3 pi over 2, and 3 pi over 2 plus pi over 6 should give me, what, 5 pi over 3, of course. And 11 pi over 6 before I get back to 2 pi, which is the same thing as 0. All right. Let's go ahead and see what happens here. So as theta increases from 0 to pi over 6, my r is going to increase from 0 to 5. So I've got the point 0, 0 on my polar graph. And when theta equals pi over 6, my r is going to be 5. So when theta is pi over 6, my r, my distance from the pole, is going to be 5 units. So I count out 1, 2, 3, 4, 5 circles. I'm going to get this point on my graph. Now when theta equals pi over 3, I'm back to the pole. And then when theta equals pi over 2, I'm going negative 5 units in that direction. So I'm going in the opposite of the pi over 2 direction. So I have to count out 5 units in the 3 pi over 2 direction. And then back up to 2 pi over 3, r equals 0. So it doesn't matter what direction I'm in. I'm going to the pole. So let's plot our journey. So from theta equals 0 to theta equals pi over 6, I'm going to be gradually increasing my angle and also increasing my distance from the pole. So as I increase my angle from 0 to pi over 6, I'm also increasing my distance from the pole. So I'm going to hit this point. Okay, so notice I'm increasing my distance from the pole. I'm also increasing my angle theta. So I'm covered here. Now, as I go from pi over 6 to pi over 3, that's going to take me from this branch to this branch. So I go from pi over 6 to pi over 3, going from r equals 5 back to r equals 0. So that's going to take me like so. So I'm covered from pi over 6 to pi over 3. Now as I go from pi over 3 to pi over 2, so from pi over 3 to pi over 2, my r is negative. So as I'm looking from pi over 3 to pi over 2, I'm looking at this branch. So really I'm going to be on the opposite side of that. I'm not going to be in the first quadrant, I'm going to be in the third quadrant. So as I look in the pi over 3 direction to the pi over 2 direction, I'm going to be getting closer and closer to this point. And then from pi over 2 to 2 pi over 3, my r moves from negative 5 back to 0. So still negative, so rather than being in the second quadrant, I'm going to be in the fourth quadrant. So from pi over 2 to 2 pi over 3, I'm going to be moving like so. All right, so that's going to be part of my graph that goes from 0 to 2 pi over 3. Now, if I look from 2 pi over 3 to pi, so 2 pi over 3, this is going to be 3 pi over 3, or pi radians. And I'm leaving the details of the math to you. We know the increment is pi over 6, so I'm leaving the details to you as far as calculating these exact theta values. So I've got 2 pi over 3, 5 pi over 6, pi, 7 pi over 6 on my way to 4 pi over 3. So if you go through the same sort of reasoning here, from 2 pi over 3 to 5 pi over 6, my r, my distance from the pole, is going to increase from 0 to 5. So as I move from an angle of 2 pi over 3 to an angle of 5 pi over 6, I'm going to have 5 pi over 6 comma 5 on my graph. Excuse me, 5 comma 5 pi over 6. All right, these are our theta coordinates. And I'm starting in the 2 pi over 3 direction here. So from 2 pi over 3 to 5 pi over 6. Going to look like so. And then from 5 pi over 6 to pi, I'm going to have the point 0 pi on my graph. I'm going to move back towards the pole. Now as I go from pi to 7 pi over 6 in the third quadrant, I'm moving from an r of 0 to an r of negative 5. So really I'm not going to be traveling into the third quadrant, I'm actually traveling into the first quadrant. But as I go from pi to 7 pi over 6 in the first quadrant, what I'm really doing is I'm retracing this branch in the first quadrant from 0, which is the opposite of pi, to pi over 6, which is the opposite of 7 pi over 6, right? I'm going in the opposite direction because my r value is negative. So opposite the pi direction is 0, opposite the 7 pi over 6 direction is pi over 6. So this branch here is actually taking me through the same set of values as this branch here. Okay? Think about that if you don't see that right away. But with that in mind, once you understand that, you should be able to see that the rest of my sinusoid is just going to retrace these three leaves of my rose curve. So now that we have the picture, it should be pretty obvious why we call this a rose curve. It's a rose curve because we've got different leaves. These shapes look like leaves. And this is the graph of r equals 5 sine of 3 theta. Now a couple of comments on rose curves. So in general, r equals a sine of n theta, r equals a cosine of n theta. These are both types of rose curves. And if, first of all, n is an integer. If n is odd, that's going to give you the number of petals. So 5 sine of 3 theta, we've got 3 petals on my rose curve. If n happens to be even, you're actually going to get double the number of petals. And the reason is that when n is even, when you do the sinusoid and you trace out the polar graph, when n was 3, right, this branch actually just retraced out something we traced out previously. That's not going to happen when n is even. So I leave that to you as an exercise to try something like r equals 5 sine of 4 theta, or even more simply, r equals 5 sine of 2 theta. And you should see that what you get has double the number of petals as the value of n. So at this point, I'm going to diverge a bit from our guided notes. And I'm going to take a look at the graph of something called a cardioid. So the cardioid r equals 2 minus 2 sine of theta. And we're going to start the same way as we did with the other examples. We're going to graph in the theta r plane. And I'm going to go from 0 to 2 pi. So if I think about 2 minus 2 sine theta, I'm actually going to rearrange this so it's a bit more familiar from what our sinusoids look like. So negative 2 sine theta plus 2, This tells me I'm going to have a baseline of 2. Amplitude is 2. So here's my baseline of 2. My amplitude is 2, but since this is negative, it's going to be flipped. So I'm not going to go over the details of really graphing this out. I'm just going to take it for granted that you guys can do this from the section on sinusoids from chapter 10. So you've got pi over 2 here. This is going to be pi over 2, 0. And then back to our baseline at theta equals pi. Then at 3 pi over 2, we're going to hit r equals 4. And then back to our baseline at theta equals 2 pi. So 2 pi, comma 2. So not a lot of time to spend on that. What I want to concentrate on is graphing the polar equation. So again, let's take a look at some polar graph paper. And what I'm going to do is, first of all, label a few of my angles here. So 1, 2, 3, 4, 5, 6. This is pi over 2. Pi and 3 pi over 2. And I'm going to label, I'm going to divide this into 4 sections, again, so we can see the 4 quadrants clearly. So quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So let's think about what's happening here. As theta goes from 0 to pi over 2, notice I've got the point 0.02 here, so that's going to give me 2 units. And when theta equals pi over 2, my r equals 0. So at theta equals pi over 2, my r equals 0. So that's going to take me back to the pole. So the first part of my graph is going to have my r, my distance from the pole, is going to gradually decrease as my angle increases from 0 to pi over 2. So as my angle increases from 0 to pi over 2, as I progress through that first quadrant, and I get closer and closer to that pole. Now as I progress through quadrant 2, my distance from the pole is going to increase from 0 back up to 2. So by the time I get to theta equals pi, I'm going to be 2 units from the pole. So I'm going to get basically the symmetric image of what I got in the first quadrant. And then third quadrant, my distance from the pole is going to increase from 2 to 4. So we had the point 2 pi on the graph here, right? This was r comma theta. And that's going to increase to a distance of 4 units from the pole at an angle of 3 pi over 2. So 1, 2, 3, 4 units from the pole at an angle of 3 pi over 2. As I keep going around like so. And then the fourth quadrant, my distance from the pole is going to decrease from 4 back down to 2. So from 4, 3 pi over 2, I'm going to curl around, get closer to the pole, and hit the same point I started at. This is going to be 2 comma 2 pi, which is the same as the point we started at, 2 comma 0. And there's my cardioid. This was r equals 2 minus 2 sine of theta. And notice, just like we investigated with the circles, when we have a cardioid involving sine, notice that this cardioid opens downward. And I'll leave it to you as an exercise, but if you look at the cardioid r equals 2 plus 2 sine theta, what you're going to get is the mirror image of that. So if you look at 2 plus 2 sine theta, you're going to get the same picture. It's just going to be inverted. So 2 plus 2 sine theta, you're going to get something that looks like this. 1, 2, 3, 4. So just a quick sketch here. So you get this sort of image for 2 plus 2 sine theta. Cardioid's going to open up or down for a sine function. And as we'll see in a few moments, the cosine versions of this are going to open to the left and to the right. Before we get to that, let's take a look at one more example. So cardioid, as I mentioned, it belongs to a more general family called limaçons. So let's take a look at this example here where we graph a limaçon. And you'll see this graph shares some similarities with the cardioid. As I said, it belongs to the same family. Let's take a look first in the theta r plane like we did for the previous couple examples. So if I look at r equals, I'm going to rearrange this 2 sine theta plus 1 so that we can see, okay, my amplitude is 2 and my baseline is 1. So I'm going to get this basic shape. I'm not going to go into a whole lot of detail here, but you should be able to identify that you've got the point 0, 1, you've got the point pi over 2 comma 3, you've got the point where am I? You've got the point pi comma 1, sorry. You're going to have the point 3 pi over 2 comma negative 1, and you're going to have the point 2 pi comma 1. Alright, so let's take a look at the polar graph here. Get some polar graph paper for us. And as you can see, one thing that's going to change for us is the fact that we actually dip below the axis just a bit. So let's tackle that in due time. So I'm going to label my quadrantal angles to start with. So I've got, this is going to be r equals 1 plus 2 sine of theta. So I'm starting at 0 comma 1. So remember this, the first coordinate goes with theta here. This is theta r. It's a little confusing when you're going from the theta r plane to the polar graph, just because you have to reverse the roles of the first and the second coordinates here. But this is telling me my distance from the pole is 1 when my angle is 0. So I'm starting here, so that first circle away from the pole. And as theta goes from 0 to pi over 2, my r increases from 1 to 3. So 1, 2, 3. And I end up with something that looks like this. Now, as theta goes from pi over 2 to pi, I'm going to have the point 1 pi on my polar graph. So again, reversing theta and r. So in polar, we have r comma theta. Here we're looking at theta comma r, so just be careful of that. Curling back around. As my angle increases through the second quadrant, my distance from the pole is going to decrease back to 1. Now here's where things get a little bit interesting. In the third quadrant, my r is going to decrease from 1 to -1. So by the time I get to 3 pi over 2, I'm going to be going in the negative direction. So what's going to happen is at a certain point, notice I'm positive for a while. At a certain point, I'm actually going to cross over into negative territory. So for a while, I'm in the third quadrant. Then my angle goes negative. And once my angle goes negative, then I'm going to be in the first quadrant. Okay? So when exactly does that happen? Well, if I look at r equals 1 plus 2 sine of theta, and I set r equal to 0, right, because that's going to tell me where my intercept is. That's going to happen when sine theta equals -1/2. So sine theta is going to equal -1/2 when theta equals 7 pi over 6 and 11 pi over 6, right? Because that's going to be a reference angle of pi over 6. So I'll leave the details of that calculation to you. Now, once we have that, that tells me that I'm actually going to hit the pole here when theta equals 7 pi over 6, and then again when theta equals 11 pi over 6. So as I move from the angle of 3 pi over 2 back towards an angle of 2 pi, my r is going to be negative for a while. So that means I'm going to be in, actually, as I travel through my fourth quadrant angles, I'm going to be in quadrant 2 until I get to 11 pi over 6 right here. So I'm going to curl around till I get to 11 pi over 6, and then I'm back to this point here, 2 pi. At an angle of 2 pi, I'm going to be 1 unit away from the pole. So it's a little bit tough to see. This is a little bit small. I could actually make this a little bit bigger by saying that each circle represents 1/2 of a unit. So if I do that real quick, so 0 pi over 2 pi and 3 pi over 2, I can draw it a little bit bigger so we can see a little bit in more detail what's going on. So if I consider each circle to be 1/2 of a unit, so this is 0.10 here, and then pi over 2, we're 3 units away, so 1/2, 1, 1.5, 2, 2.5, 3. So this is 3 comma pi over 2 in polar. And 1 pi, so I'm going to be doing something like this. Now, when theta equals 7 pi over 6, I'm at the pole. So here's 7 pi over 6. Tells me I'm going to be at the pole here. Here's the opposite direction of 7 pi over 6. So from 7 pi over 6 to 3 pi over 2, we're going to be moving towards an r value of -1. So the 3 pi over 2 direction, r equals -1. So I'm moving from pi over 6 direction to the 3 pi over 2 direction. And then I'm going to do the same thing in the fourth quadrant as I move from 3 pi over 2 to 11 pi over 6. Then I'm going to come out just past the 11 pi over 6 direction back to my point r equals 1, theta equals 2 pi. Right? So this is what they call a limaçon with inner loop. So you can see the inner loop there. Contrast that with the cardioid where it looked more like a heart. It just came to a point. So we'll take a look in GeoGebra real quick at some examples with the cosine family of limaçons. Alright, this is GeoGebra's graphing calculator app, and we're going to use it to investigate the cosine family of limaçons, 2 plus b cosine of theta. So what I'm going to do is enter that in. I'm going to enter in r equals 2 plus b times the cosine of theta. And when I hit enter on that, you should be able to see that I get a graph when b equals 1. So you can see that this is something halfway in between a circle and a cardioid. If I show you when b equals 0, we'll get a circle of radius 2. That's because r equals 2. We saw in the last video that's just a circle of radius 2 centered at the pole. So I'm going to hit play on this and we'll see what happens as the value of b changes from -5 to 5. You can see when b equals 2, we get that cardioid. As b gets larger, we get that limaçon. As the larger b gets, the bigger that inner loop got. And then as b goes negative, we get the same thing on the left side of the y-axis. So b equals -2, we get the cardioid. As b gets larger in the negative direction, we get limaçon with a larger inner loop. And we should be able to see as b gets back to 0, we get the circle, cardioid at b equals 2, limaçon with growing inner loop as b gets closer to 5. So you can see what happens with the cosine family of limaçons. When b is positive, opens to the right. When b is negative, opens to the left. And if you repeat the investigation for the sine family of limaçons, you'll see the same thing up and down. So the last type of graph that we want to take a look at in this section is the lemniscate. And you'll notice that it looks a little bit different than some of the ones that we've looked at before, namely because we've got r squared on the left-hand side instead of just r. So what I'm going to do to start is note that ultimately we're going to be looking at, if I take the square root of both sides, we're going to be taking a look at r equals plus or minus the square root of 4 cosine of 2 theta. So the game plan here is, let's look at 4 cosine of 2 theta, and then let's think about what happens when we take the square root of that. So let's look at the graph just in the theta r plane of 4 cosine of 2 theta. So there's my theta r plane. And I'm just looking at r equals 4 cosine of 2 theta. And this is actually a pretty straightforward graph. It's a cosine function. The amplitude's going to be 4. And period is going to be just pi. That's 2 pi over 2, which is just pi. So I'm going to leave the fun details to you guys. This is just review from the section on sinusoids. Basic shape of my graph is going to look like this. Increment is 1/4 of the period, so pi over 4. So pi over 4, pi over 2, 3 pi over 4, and pi are going to be the key theta values here. Now, this is just 4 cosine of 2 theta. So what's going to happen when I take the square root? Well, when I take the square root, anything that's negative isn't going to be a part of the graph when I take the square root, because I can't take the square root of a negative number. I'm not going to get I involved in this section. So the domain here, if I restrict my attention to 0 pi, the domain is going to be just from 0 to pi over 4, and then from 3 pi over 4 to pi. So let's see what happens. When I take the square root of this, still looking at the theta r plane, I'm going to get r equals plus or minus 2 radical cosine of 2 theta. So if I think about taking this curve and taking its square root, well, the square root of 4 is going to be 2, so instead of the point 0.04, I'm going to have the point 0.02 on my graph. And likewise at pi over 4, I've got r equals 0. If I take the square root of 0, I'm going to get 0. So instead of decreasing from 4 down to 0, when I take the square root, I'm going to be decreasing from 2 down to 0. And likewise from 3 pi over 4 to pi, notice on 4 cosine of 2 theta, I'm increasing from 0 to 4. Likewise, when I take the square root, I'm going to be increasing from 0 to 2. Now, that takes care of the positive version of this, but since I took the square root here, this requires a plus or minus sign. So I also need to consider negative values. So if I take the square root of this with a negative sign out front, instead of decreasing from 4 to 0, I'm going to be increasing from from negative 2 to 0. So notice this is not a function, right? This is plus or minus 2 times the square root of cosine of 2 theta. So I have plus or minus, and I'm going to have the same thing here. So this is still the theta r plane. This is not a polar graph. This is a Cartesian graph. This is what I'm going to use in order to get the polar graph of my lemniscate. So clearly not a function. That's okay. We're not interested in the Cartesian graph anyway. So let's think about what this means for the polar graph. So I'm just going to sketch out a graph here. So it seems like pi over 4 and 3 pi over 4 are going to be key directions. So I'm going to sketch out pi over 4, both sides, 3 pi over 4, again, both sides. And I'm going to label this 1, 2, 3, and 4, because I want to think about each of those 4 parts of my graph separately as I graph this lemniscate. So for part 1, as my angle goes from 0 to pi over 4, my r value, my distance from the pole, is going to decrease from 2 to 0. So if I consider this to be 0.20 in polar, as my angle increases from 0 to pi over 4, my r is going to decrease from 2 to 0. So that's branch 1. On the other hand, for this branch, when I'm in the 0 direction, I have the point -2. So this is -2 in the 0 direction. It's going to be going in the pi direction. And as theta increases from 0 to pi over 4, I'm actually going to get closer to the pole that way. So the negative pi over 4 direction is over here. So rather than being in the first quadrant, I'm in the third quadrant. I'm going to get something that looks like this. So that's the second branch. This corresponds to branch 2. Now let's turn our attention to branch 3. From an angle of 3 pi over 4, I'm starting at the pole. Then as I go to an angle of pi, from 3 pi over 4 to pi, my distance from the pole increases from 0 to 2. So I'm going to go from the pole to the point 2 pi, 2 comma pi. So I'm going to have something that looks like this. Right, so -2, 0 we know is the same as the point 2 comma pi. And this corresponds to branch 3. Now if I think about branch 4, and I do the same thing only in the fourth quadrant, right, because now we have negative values from 3 pi over 4 to pi, so that's going to correspond to this region in my fourth quadrant. I can draw this, and this is going to correspond to branch number 4. Now, if you remember what I said in the first video, a lemniscate looks like a figure 8, and that's what we got here. So this cosine lemniscate looks like a figure 8 horizontally. If you look at a sine lemniscate, well, I'll let you take a look and investigate that on your own. So look at r squared equals 4 times sine of 2 theta, and see what you come up with on your calculator. Better yet, check it out using the same method we just did here for the cosine lemniscate. Now, I'm going to do one example that is an inequality. You have a few examples in your book. Example 4 in this section, so example 11.5.4 you'll want to take a look at. I'm just going to go through one so you have it. So you have some problems that look like this. So graph the set r comma theta, theta between pi over 2 and 3 pi over 2, and r is less than 2 minus 2 sine theta. Now 2 minus 2 sine theta, you might remember, is the cardioid we did earlier. So 2 minus 2 sine theta is the cardioid that we looked at here. So I'm just going to sketch this out. I'm not going to be real precise here. But notice that this is a less than sign. So if you remember from doing inequalities by graphing in the past, I don't actually want to include the cardioid. I'm just going to do a dotted line here. So this is my cardioid. R equals 2 minus 2 times the sine of theta. And I'm interested in angles between pi over 2 and 3 pi over 2. So here's my angle of pi over 2. Here's my angle of 3 pi over 2. So I'm going to shade the region inside the cardioid between angles of pi over 2 and 3 pi over 2. Now, why am I shading the inside of the cardioid? I'm shading the inside of the cardioid because of this less than. So what is this saying? This is saying the distance from the pole is less than that of the cardioid. So I'm looking for all the points that are closer to the pole. So closer to the pole than the cardioid. So that's why I'm shading the interior of the cardioid here. Now, if this was less than or equal to, then I would have the boundary of the cardioid included, but only the boundary of the cardioid for the angle specified, just the boundary between pi over 2 and 3 pi over 2. So again, take a look at example 11.5.4 in your book for more examples about inequalities. So with that, that gives us a nice introduction to the graphs of some of these basic polar curves and some inequalities dealing with them as well. In the next video, we'll take a look at finding intersections of polar curves, and that will complete our study of section 11.5. Till the next video, see you next time.